pointer. No. Slideshow. Okay, I think it's time to start. So any question from this time? This time I think we finished 1.3, which told you basic matrix or arithmetic rule. So I told you how to do matrix addition, matrix multiplication, and how to multiplication of a scalar, etc. And if there is no question, then let's go to the next section, 1.4. So some matrix algebra. So as we said, we talk about what's matrix addition and what's matrix multiplication, and this multiplication by scalar. And just like addition and the multiplication for scalars, there are quite a bit of a rule for matrix. So you can see there is this, you can swap the order. I forgot the name. So addition is commutative. So a plus b equal to b plus a, and addition is also associative. So a plus b then plus c equal to a plus parentheses b and c, and multiplication is also associative, and and also this multiplication and addition is what is it called? Distributive. Yeah. So you see that most of these are just what you expect. Scalar multiplication and let me try to get this up. Yeah, so most of these are just like scalar multiplication and addition rules you expect, except that the multiplication is not commutative, as we said. So AB not equal to BA. Not necessarily, most of the time. Yeah. And anyway, so those are rules, and we will see some of them and do a little easy proof. Okay. So yeah, let's see some example. So we have ABC like this, and you can do brute force calculation to check that A and BC equal to AB and C. So A like this and BC, so let's check some entries to make sure we are not wrong. So maybe this one, so this is minus 3 times 1 plus 2 times 2, so this is minus 1. So etc. And you do the multiplication, then you find out that those two are equal. And yeah. And moreover, A of B plus C equal to this thing, so B and C is this, and yeah. So you can do the brute force calculation and check it out, they are all the same. And then let's do a more general proof of this. And so here we have a lot of notation. So we have A and its entries as small aij, B and its small entry as bij, C and cij. And as we say, we are kind of dumb, so we need a name for every product. So we have D as A times B plus C and E as AB plus AC. So we want to show that D equal to E, so we want to show every element of D equal to every element of E. Okay? And so we think about what's the element of D. So we skip a few steps, but you think about the element of B and C. And as we said before, so the addition is just entry-wise addition. So the kj's element of B and C should be just bkj plus ckj. And then you do matrix multiplication, then it should be this. So the ij's element of this thing should be summation k. So there is a dummy thing getting sum over this k inside. And okay. And the idea is that let me draw. So once again, the idea is that we have our matrix multiplication. So this is n by n, and then you have n by, so this is n, n by n. Oh, yeah, let me try to draw better. Oh, yeah, wait, okay. Anyway, this is n by n, and you have n by r. Then we are saying that each element is you are summing over this row in the product with this row, right? So this summing over k is this you are moving on this row and this column, that's this k. Okay. And yeah, so this is ij. So the ijth element of this product is the first matrix is ik element, and times the second matrix, the kjth element. So this moving is like k is here, yeah, and you are summing k from 1 to n. Okay, so that's how you write in an algebraic way the matrix multiplication. So like entry-wise matrix multiplication is written in this way as a reminder. And anyway, so that's the ijth element of this algebraic expression. So aik times bkj plus ckj. And then we can also have e of the ijth element of e. So we have a times b here. So once again, the ijth element. So it should be the ijth element of this plus the ijth element of this. And the ijth element of this is once again aik plus times bkj and summing over k. And here you have aik times ckj summing over k. And then are those two things equal? Then yes, because we know the summation is linear. Because those two things, or yeah, or because so here we have just a scalar multiplication. So you can just multiply this out. Then this is summation of AB plus BC. And then summation you can always break out into two summation. So this is equal to this. And that means all the element of D equal to all the element of E. And so this is equal to this. Okay? So this is a very long proof of something you probably think is obvious. And then let's prove something a little more non-trivial. So rule 3, we didn't have rule 3 here. Let's write down. So it should be, we're trying to prove that AB times C equal to A times BC. Okay. And yeah, once again we need to do extra names. So let's call this AB as D and this BC as E. Okay. And once again, matrix multiplication rule. So the ijth element of this AB is some aik and oh, okay. We need more dumb variable, so we call this IL's element. So this is ik times aik times bkl, and k sum from 1 to n. And similarly, we have this e here. Okay. And something important. So the second dimension of A needs to be the first dimension of B, so you can do multiplication together. And this second dimension of B needs to be same as the first dimension of C. Okay, so that's important to note. So this n equal to this n, and this r equal to this r. And anyway, so then you have multiplication of BC. Then it's the same thing, but you are summing over L here. And yeah, because you are multiplying BC and the shared is dimension R, so you are summing to R. And anyway, so that's the element of AB and element of BC. Then you can do more multiplication by writing out the expression. So finally, we want the ijth element of this whole thing. And so ijth element, so you want to multiply this with C, and so you're summing over another L and CLJ. Okay, and then if you express all this summation, d summation, and it's like this. So summation k side and then summation l. And similarly, you have similarly on the ABC side, you have this AIK and EKJ. Okay, so like this. But yeah, but you can easily see that those two things are the same because you can put the A inside the summation and the ordering of summation doesn't matter. And yeah, so like this. We are doing this in other way. So anyway, so the ordering of summation can be changed, and then you can just and then you see that this A okay. So we do a lot of things here. So the ordering of summation doesn't matter. Then you see A doesn't depend on R, so you can pull A out of the summation. So it's like this. And yeah, then that means that ABC equal to ABC. Yeah. Any question about the proof? So this is how we rigorously prove that this rule, because we say for any ABC that parameterized by those coefficients, we can prove that every element of this equal to every element of this. Okay. So yeah, so this is a pretty simple proof, but we are doing this to get you familiar with those algebraic multiplication kind of proofs. Okay? And yeah, once again, there are a lot of rules, and I think they are pretty intuitive, but if you want, you can try to memorize them. Yeah. And yeah, and of course, if you want some practice, then maybe we'll do some homework. You can try to prove some of those in this kind of entry-wise algebraic proof. Okay, we're a little slow. Okay, so let's talk more things. And notation. Okay, so for now this is just notation. So we can have powers of A. Well, we have multiplication of A. Obviously, we can have integer power of A. So so A to the kth power, you just multiply A with itself k times. So right now it's just a notation. And we can see some cool example with a little structure. So A is this 1, 1, 1, 1. Then you found out that A squared is 2, 2, 2, 2, because every one of them is 1 plus 1. Okay. Then A cubed is 4, 4, 4, 4. Then yeah, and in general you can find out that A to the n is 2 to n minus 1, 2 to n minus 1, 2 to n minus 1, 2 to n minus 1. Okay? And for now, this is just a notation and you can remember. Then let's talk about more important thing, identity matrix. So identity matrix is the identity for matrix multiplication. So and it's an identity on both left and right. Okay, here we are writing this a little weird. Okay, I don't like this, so let's rewrite this. So this is actually two lines because we are not saying A is a square matrix. So IA equal to A for A, and BI equal to B for B. Okay. Okay, so it's the left identity for every matrix, and it's the right identity for every matrix. And so what is this nice identity matrix? There are a lot of them. So because A can have different dimension, B can have different dimension. So we kind of skip the dimension of A and B here. And anyway, identity matrix is parameterized by this integer. It's always a square matrix, it's n by n matrix. And if you write down its entry, then it's a little ugly form. So the entry is delta ij. So it means that it's 1 only when I equal to j, and 0 when I not equal to j. But I think it's easier to see an example. So identity matrix looks like this. So it's on the diagonal it's 1, and on the off diagonal it's 0. And it's 3 by 3, and you can easily you can easily see like extend this to more, right? So if it's 4x4, then just get extra 1 here and then more zeros. And yeah, so that is this expression right now in a matrix form. So the ij's entries is 1 only if I equal to j. So only on the diagonal is 1, and everything else is 0. Okay. And yeah, so maybe let's draw a picture. Yeah. Sorry. Yeah. So maybe I'll draw a picture here. So 1, 1, 1, 1, 1, da da da, and 0, 0, like this. Okay. Question about definition identity matrix? No. And let's see some rule. Okay. And yeah, so identity matrix multiply on the matrix to get itself. And I guess let's do a little check. So this element, it should be 1, 0, 0 times this 3, 2, 0. So this is 1, pick out this 3, so it's back to this 3. And here, this element is the same, so 1, 0, 0 times this 4, 6, 1, so this 1, pick out this 4. And similarly, let's choose an element, maybe this 3. So is this 0? Yeah, oh, okay. Yeah, so it's 0, 1, 0 multiplied by this 1, 3, 8. So this 1 will pick out this 3, so go back to this 3. Okay? And yeah. And anyway, so yeah, and on the left side, yeah, the similar thing happened. So you can see that yeah, so maybe I'll see the first column. So this first column will basically pick up by this 1, 0, 0. So this 3 will be 3, 4, 1 times 1, 0, 0, and this 3 pick up by this 1. This 2 is similar, this 2, 6, 3 with this 1, 0, 0, so 2 with 1 back to 2. And the 0, 1, 8 multiplied by this 1, 0, 0, so this 0 picked up by this 1, so it's 0 here. Okay. Then the next column is similarly picked up by this 0, 1, 0. Okay, so we do, and obviously you can once again write down the algebraic proof, but I'll skip. You can rigorously prove the identity matrix is actually identity for any matrix. And here here is a special case where A is a square, but this also works for, so maybe I should write here. So A like n by n matrix, and B n by n matrix, they also work. Yeah. So any size matrix, as long as you identity matrix dimension match. So if you want to have, so then if A is n by n, then you need like im here, and B is n by n, then you need to have n dimension identity matrix here, so you can actually multiply it. Okay, so that's identity matrix, and yeah, here we have yeah, as we say, so we can have any dimension B and C, and then you have this left identity and right identity, and we're writing in a funny way. Anyway, so here we're n by n, n by n, yeah. And as we said, the identity matrix, they are those these diagonal ones, and if you cut them into columns, then you see each column is like the standard basis vector, those EJ. So it is 1, 0, 0, 0, 0, 1, 0, 0, 0, etc. So it's all 0 except 1 and 1 of the coordinate. And those vectors, we call them EJ. So if it's 1 everywhere, and just on the jth element is 1, then it's called EJ. So let's write this EJ. So EJ equal to this vector of 0, 0, 0, 0, 1, 0, 0, dot, 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 0. And this is the jth element. So on the jth element is 1. Okay. And yeah, so this is just another way to write an identity matrix. So it's a whole bunch of columns with those EJ and E1, E2 to En. Okay, so that's identity matrix. It should be easy. Then we're going into more interesting part, matrix inversion. And yeah, so now we have a 1, then we can think about the inverse of matrix. So like in a real number, the multiplicative inverse of your real number is a number such that you multiply back into 1. Okay, and we know any non-zero number a has a multiplicative inverse that's like 1 over a. Okay, then what's the matrix inverse? And now things get a little bit tricky. So we say every matrix can be multiplied by the identity matrix. But for matrix inversion, we restrict back to the square matrix. So we only talk about matrix inversion for n by n matrix. Okay? Yeah, you might be able to generalize to more, but it's tricky. So for now, for the easiness, let's restrict into n by n matrix in this course. Okay, and or for now. And anyway, so we talk about matrix inversion only for n by n matrix. And so matrix is invertible or non-singular. We'll see why it's called non-singular later. Anyway, so it's invertible if there is inversion. So there is a B such that AB equal to BA equal to identity. So there is a B such that you multiply A with B, then you get to identity. And this B is called a multiplicative inverse, or more generally, we just say B equal to A minus 1. Okay? And okay, and here we actually squeeze in some theorem here. So there is a theorem that's pretty hard to prove, so we will not prove. So because remember we say that matrix multiplication are not commutative. So AB not necessarily equal to BA, but AB actually equal to BA when B is A's inverse. Okay, so this is a theorem that's pretty hard to prove. Such says that for your H is A, if you have right inverse B such that AB equal to identity, then you multiply B on the right side of A, then it's also identity. So if AB equal to identity, then BA will also equal to identity. Okay, and obviously you have a similar thing. If BA equal to identity, then AB equal to identity. So here we have like two equations to check, but actually you only need to check one of them. If AB equal to identity, then B is the inverse of A. Okay, and yeah, so that's something subtle. And then okay, so we can wave over this left inverse and the right inverse thing, and then we can prove that the inverse is unique. So there's almost one inverse, pretty easy now. And the proof seems kind of dumb, but this is how you rigorously do it. So there is some B such that BA equal to AB equal to AB. BA equal to identity, and there is a C. Which one do we use? Oh, we are very okay. Yeah, we're kind of careless. But anyway, so B with AB equal to BA equal to identity, and C with CA equal to AC equal to identity. Then we can have B. Then so B should be equal to B times identity. Okay. So B should equal to B times identity because that's how identity defined. Identity times everything on every side is identity. Then we know identity equal to AC because we have AC equal to identity. And then we know multiplication is associative, so this B times A times C equal to B times A times C. And but we know BA is also identity, so this is identity. So as identity times C should equal to C, so we know B equal to C. Okay. Yeah. So this kind is a little dumb, but this is how you prove that if there is something that's inverse of A, then and another thing that's inverse of A, then they must be equal to each other. That means that the inverse is this inverse of A is unique. Okay. And we just write it as A minus 1. I guess I should prove this first, then write this, because usually by this notation we mean that it's unique. So you just write it as one matrix instead of a set or something. Okay. And anyway, that's definition of inverse. Any question? And we will give an example that's not too intuitive, but anyway. So we have a matrix here, and we can, this is the inverse. I guess we can try to do the checking, but okay, it's pretty hard. So this 1 is, so 1 over 10 with minus 2 plus 12. So minus 2 times plus 12 is 10, so 1 over 10, then over 10 is 1. And this element is 1 over 5 with 4 minus 4, so it's 0. And this element, once again over 10, is minus 3 plus 3, so that's 0. And this element with 5 and 6 minus 1 is 5, so divide by 5 is 1. Okay? And I guess here, the more interesting thing is we can check this right inverse is also a left inverse. So then let's do this again. And okay, so now you see it's actually hard. So 1 over 10 with minus 2, and then 1 over 10 with 4 times 3, so it's 12. So once again, it's 12 minus 2 equal to 0, equal to 10. And now this element, we do 1 over 10. Okay, so let's make us a little easier. And so this is 4 over 10, and this is minus 2 over 10. Okay. And this is 0, so it's, if we do 1 over 10, then it's minus 4 plus 4. Okay, so that's 0. And this is 0, then it's 6 and minus 6. Okay, so that's 0. And finally this 1, and this is 3 times 4, 12, and minus 2 times 1, so 10. Okay. So so you see that it's actually inverse, and it's both left and right inverse. And then there is more example, but anyway, you can do the brute force checking and see that it's actually inverse. Okay, so you have this triangular matrix, and you have this inverse, also a triangular matrix. And I'm getting lazy, so let's skip that. And okay, and now the important thing here is that sometimes the matrix don't inverse, and here there is a very good example. This A equal to 1, 0, 0, 0, it has no inverse, and it's basically because you have a 0 here. So I guess much later part of the course we will see what this 0 means. You don't have an inverse. But here we can just try to do a brute force proof. So we say that, okay, if we have an inverse, well, it's going to be a 2 by 2 matrix, so it's whatever B11, B12, B21, B22. And let's just multiply this with A. Okay? And you see that is 1 will pick out the first column, give you this B11, B21, and the 0, 0 vector will just give you 0, 0 here. And so you see that this thing can never be 1, 1, because you have a 0 here, and you have 1 here, and 0 will never equal to 1. Okay. So this matrix A has no inverse, and it's called singular. Okay. And as we said, this is a very important concept, and you should see this a lot more times in the course. And yeah, and here is some intuition on the singular matrix. And so for scalars, there is one number that don't have inverse, that's 0, because you cannot divide by 0. But for matrix, there are many matrices that are singular. And we can kind of see from this example that it's singular is also because it has a 0 somewhere, but this somewhere we cannot define now. Okay, so right now we just have a very vague idea that it's singular, you have a 0 somewhere. For example, you have a 0 here, then it's singular. Okay, and you can kind of see, so what do I mean by 0 somewhere? So if A is like 0, 0, 0, 1, then it's probably also singular because you have a 0 here. Okay, and yeah, but for now, the technical definition we have for singular is that there is no inverse. Okay, and this is just a vague intuition. Hopefully, don't confuse you too much. Okay, any question? Okay, if not, then let's have something interesting. So inverse of matrix, and we can have an inverse of a matrix, and we can have an inverse of a product of a matrix. So you have A and B both non-singular, so if both of them have inverse, then AB will also be non-singular and they have an inverse. Okay. So this AB inverse is actually equal to B inverse times A inverse. So so you inverse everything, but you need to invert the ordering. Okay. The inverting ordering is kind of interesting. So this inverting ordering is something you don't have in scalar because in scalar multiplication ordering doesn't matter. But in matrix, then you need to inverse the ordering. And we can prove that this is actually inverse of AB. And well, here you can see why we want to invert the ordering. So B minus 1, A minus 1 times AB, then equal to, then because things are associative, so you can deal with this A minus 1A first, and that's identity, then identity you can get rid of, then you got B inverse B, then it's identity. And you can also prove that it's left inverse by similar proof. So you deal with this B minus 1 and become identity, then A minus 1 become identity. Okay? And yeah, in general, you can get this longer, and you have a string of matrix multiplying together, and the inverse is the same string with different order and all inverse. Question? Okay. And the next thing is kind of different. Okay, so we have a small digression from these inverse things, and we define another operation. Looks a little similar, but actually very different. So it's a transpose. Actually, we already talked about transpose. Sorry. Yeah. So now we talk about transpose, and we have some rules for transpose. And so remember, transpose is like you. Okay. So here we have an example of transpose. So A is this, and A transpose is this. So we basically flip the row and the column. I like to think about you flip through a diagonal, so you see the transpose. So like this is 5 and 4 got swept, and this 2 and 1 got swept, etc. Or you can think about this row flip to this column. Okay. So then, because you flip row and column, then you flip again, then you back to your original matrix. So if you do transpose twice, you just get it to yourself. And then there is linearity. You can easily check. If you multiply by alpha, then do transpose is same as you do transpose and multiply alpha. It's pretty obvious because alpha is multiplying every element, and that commute with your swapping order. And also this addition commute with you doing transpose. So you can add together, then transpose, add together. It's the same. And the more interesting thing is this. So AB transpose kind of like the inverse equal to B transpose A transpose. And yeah, once again, you can write down this proof. Actually, maybe I can write this down very quickly. Okay, sorry. I guess let's see example first. So example, we have AB transpose, AB equal to this thing. So so here we have like this element of AB will be the row of A times the column of B. Okay. Then we think about the transpose of this thing. So this A, excuse me, is 8 get transposed to here. Then it should be equal to the B transpose times the A transpose. Because you have a B transpose and this column becomes this row and this row becomes this column. Okay, and okay, yeah. So let's not do that. Yeah, and obviously you can also write this in. You can also write this in algebraic, so you can think about what's A, B transpose, and what's this ij's element should equal to what, and finally you should get to like BT. Yeah, you can write this element wise and try to prove this one. Okay. That's something you can do maybe in homework. And finally, so small reminder. So we talk about matrix multiplication rules, or more like matrix multiplication and addition rules. And yeah, they satisfy most of the scalar rules except multiplication is matrix multiplication is not commutative. And we define those identity matrices. There are actually a lot of them there is one for every dimension. So there are n by n matrix. And from the identity matrix, we have the matrix inversion. So we define those A minus 1 is actually unique. So for invertible matrix A, then we have this A minus 1. And we know that A minus 1 times A equal to A times A minus 1 equal to identity. And then if A and B are both invertible, we know AB is also invertible and invert into this. And then we have this very important concept of a singular matrix. And for now, it's defined as a matrix that's not invertible. So we cannot find A minus 1 such that A minus 1 times A equal identity. And also we have rules for transpose. And the most now the trivial one is this AB transpose equal to B transpose times A transpose. Okay. Okay, we have 2 more minutes. Maybe let's have a break now, and we'll talk about 1.5 next class. Yeah, so we'll start 2 minutes earlier next class. Okay.
我想问功课的这个第3小题要画什么？我们没有 M， 也没有它的坐标。
Geometric interpretation and 就随便假设个 M 吧，应该是对，我看一下，
随便假设 M 和坐标画出它的关系就好了吧？
对啊，就大概示意图的感觉，应该是对 x1 跟 x2 画。我再看一下，回想一下问题。对啊，应该是。对啊，就跟上课有点像嘛，就画2条线这种感觉。对啊，应该是对 solution set 画线这样。
第4题的题目我看不太懂，它要做什么？
第4题
就是 A1、A2、A3 都是什么？然后为什么它可以写成这样？
A1、A2、A3 应该是那个 color matrix of A。对啊，就是 A 我可以直接画嘛？用这个画。对啊，应该是说 A 是5×3嘛，所以是说 A 是这样子 A1、A2、A3 这样子。对，然后你再去正下面的东西。
了解了，好，谢谢老师。
就是刚刚这一页好像这里有写
说。对啊，因为我后来改了，所以多了。等一下我会上传，因为我常常会 update。
基矩阵会至少含一个零。就是。
这要扯到后面的观念，基本上是那个要说的是 eigenvalue 里面有零，但是对啊，我们现在还没有这个观念啦，所以。
因为我记得高中学的基矩阵第一。
基矩阵，你说的基矩阵是什么？是 eigenvalue 吗？因为中文我不太知道。
就是 singular matrix， 就是如果它长这样。
就如果它是diagonal的话，就是 diagonal。
就它长这样，它好像也是。
对啊。这个是 singular 吗？这个好像不是 singular 吧？高中的话，你应该首先我们等一下下一章要教应该是那个行列式等于零吧 ，determinant 等于零，它是行列式，它是 singular 的。但是这个 determinant 应该是2吧，因为它是1减-1是
2。对好，那是我记错了。
对，你记错了。
你上次提到这个问题，要怎么去想？要怎么解释？
怎么解释？好吧，正名的开头，因为我现在不太记得。正名开头通常应该是说，一个 matrix 是 reduced origin form， 然后另一个 matrix 是 reduced origin form， 然后你去证明说这两个 matrix 每个地方一样。然后我觉得要分析的话，可能就要去数一下 lead variables 哪些，然后 free variables 哪些之类。因为他们 equivalent 嘛，所以你会说他们 solution set 一样，所以可能就开始数 variable 啊，就说什么至少 free variable 的数量要一样嘛，然后你可能说他们的位置要一样这些事情。
我想怎么证明？
我想看怎么证明。我觉得我会 ，OK， 我这样可能有点瞎扯，但是我应该会说有 lead variable 跟 free variable 嘛，你有两个 row reduced origin form， 那他们各自有 lead variable 跟 free variable， 然后我会说，把两边的 free variable 都设成0的话，要一样之类的，我想不清楚。但总之，如果你真的想要证明的话，网络上都找得到，你可以去 Google 看看，因为是还蛮有名的。
这个不是很懂它的意思。
然后就是实数空间概念，就有点像你平常在说一维空间、二维空间、三维空间嘛。有一维空，例如说二维空间嘛，你不是有这个 x y 吗？例如说R2是这样子的 x y 的东西吗？这样子，我们不是说每一个 x y 点，例如说是 A 跟 B 嘛，然后你就可以说，那这个东西上面所有东西写的 A 跟 B 都是实数嘛，那我们就把 A 跟 B 放到不同的位置上面，写成一个跨的位置上 A、B。对啊。
谢谢。
有点看不懂他题目。
OK 这个我就写在黑板上好了，因为这是我们用的 notation 啦，因为我们有一个把 A 拆成 column vector 的东西这样子 ，A1、A2、A3 是 A 的3个 column 这样子。对。
那所以他题目是在，他题目的意思是想要表示说 x 的答案会是这样。
为什么啊？没有吧 ？A 他不是说 B 等于 A1 加 A2 吗？
对，所以它是 B 就是那两，就是3个 column 一样的意思。
对，不是。 B 应该是个5个 dimension 的 matrix 嘛 ，A 是5×3嘛，所以这个里是5，然后这里是3，然后3个被我们切成3个 vector， 然后他说 B 是等于这两个相加又等于这两个相加。
他的意思就是
对，哦。A1 跟 A3不一定一样，但是，因为我想想看，我混了，想看A1 跟 A3，应该一样吧？对，所以就是你说的，所以是等于是乘上 x 是如果110，然后把前两个换成表现。对，所以 A1 跟 A3可以一样多钱，但是对啊，但是然后你要去除它的。
所以是用定理去证明它是分解。
这个应该是说。比较简单的说法就是，那你就发现 x 至少有2个解了。
哦，这是他的意思。
然后你可以，我其实有点不太懂，因为它其实这题目有点模糊。但是没有，但是至少可以说的事情是我们是分，我们说解的数量可能有3种嘛，你们还记得吗？
然后没有解跟。
对，所以有一个或者是infinite，或者是没有嘛。那所以至少你可以回答出现在是哪一个。
但这个作业直接把这个档案上的那些认上面就可以。
这就是总之助教可以拿到就好了，所以可能你们跟他可能。对，所以
他要用定理去推说它可能会是哪一种情况。
没有，其实你这样理就已经可以直接推出来了，就是因为它有2个解，所以它就不会是一个解，对，所以它有无限多个解。
就这样。
好怪。
对，但是如果我觉得其实可以说多一点的事情，如果你也努力的话，但是我们可能评分的时候不用听到那么多就是。对啊，因为只是问 number 吧 ，number 的话那就是有2个，那就不是1个。但是如果你努力一点的话，也可以试着去找出来这个5000多个是哪些东西。对。对，那我这里修一下好了。所以我们知道 ax1 等于 b， 然后 ax2 也等于 b 嘛。就是你找出来的是 x1 x2，那个100，然后我们知道 x1 不等于 x2。然后 OK， 因为这个跟大家等一下要做的事情有点像，所以修一下。所以这里我们可以做什么奇怪的事情？我们可以把这2个相减的感觉。我们可以说 a of x1 减 x2 等于0。对吧？然后这个是个不等于0的东西，所以我们有一个 non-trivial 的homogeneous solution 在这里。所以这个东西我们可以写出来，这样写的话1/0负1，对吧？因为基本上是说我们刚刚有第一个 column 跟最后一个 column 嘛，所以 a 乘以这个等于0。那这个有什么好处呢？这个东西给它个名字叫 x3好了，这个是 x3。ax3 等于0的话，那 a 乘以任意的 x3也等于0，a 乘以一个 alpha x3也等于0。alpha， 对吧？用两边乘任何 alpha 贝塔也等于0。所以说这样子我们就可以找到无限多解，因为 对，可是这是等于0的，我们要等于 b 的，可是我们可以把这个阿法加回来，所以我们就发现，如果我们把这个阿法 x3 再加回 x1，所以 a 乘以 x1 加阿法 x3 等于0 for 阿法。所以那我们就找到我们的无限多个解了，它这个阿法线上的任何东西都是解。
为什么 a 法？为什么那个不会等于 b 啊？a x1 是 b， 然后 a 阿法 x3 是。
因为你加一个等于0的上去嘛，你把这个加到这里，对不对？
他是说那里。
因为我们刚刚说 distributive rule 嘛 ，a 的乘以 x1 加阿法 x3 等于 a x1， 然后这是等于 b， 加上 a 乘以阿法 x3 等于0。
所以那边应该等于 b 吧？
哦，对，等于 b， 抱歉。对，这个等于 b， 我们想要的是等于 b 的东西。对，所以这样子的话，你就会找到无限多个解。那等一下我们会做类似的事情。
所以我还想问一下，像这种题目啊，它的 unknown 它是3，
对啊，还有点奇怪，对啊，还是算3个好了，有点奇怪的题目。我们是不是差不多该开始了？对呀。他们是问那个5×3那个，问第4题，没有解的。
不是 ungraded 的，所以是 ungraded 的，所以我对那题没印象。
应该是 graded 的吧？他们问好像是 graded 的。好，我们等一下再讲。Okay. Sorry for late start. Okay. So any other question? If not, then yeah, let's go to next section. Okay, elementary matrix. So remember in 1.2 we were solving the linear system of equation with the coefficient matrix and the augmented matrix. And but now we have this matrix notation. We try to rewrite everything in more formal way. Okay. In these matrix algebra notations. And first we say about equivalent system. So we think about a linear system written as this ax and b. And then we multiply both sides with non-singular. Okay, so it's important that it's non-singular. So we multiply both sides by a non-singular matrix M. And you can get a different equation. So MAX equal to MB. So you can think about, you can multiply this MA equal to another coefficient. This MB equal to another, I guess, solution vector. Okay. And we say that those two things are equivalent because the solution set of the first one will be a solution set of the second one. The solution set of the first equation will exactly equal to the solution set of the second one. And and obviously if x is a solution to ax equal to b, then it's also a solution to this. And but if x is a solution to the second one, y is a solution to the first one, then here we use that m has an inverse, because then you can multiply both sides with the inverse of m. Then we see that if x hat is a solution to the second equation, then you see that ax hat also equal to b. So it's also a solution to the first one. Okay. And so we say that those two are equivalent because they have the same solution theta x. Okay. So maybe let's write a little more. So equivalent means solution set x is the same. Okay. And and we can do this many times. So we can multiply by m, then we can multiply by another one. So if we multiply by a string of non-singular matrix, so E1 to EK, and then we are still getting an equivalent system because every one of the multiplication is equivalent. Okay. And yeah, so they are all equivalent because they all have the same solution set. Okay, so this is important thing here. Same solution set. You should mark red. Okay. And yeah. And then remember in 1.2 we solve things by doing row operation. And then we can change out row operation. Yeah, we can rewrite that row operation as the matrix, and it's called elementary matrix. Okay, so instead of doing row operation, it's kind of not very rigorous. Now we can think about row operation is you multiply both sides by some matrix EI. That's non-singular. Okay, and yeah, so we'll have those elementary matrix that corresponding to row operation. And how you calculate them is you do the row operation on the identity matrix. Okay, so I guess the identity matrix is kind of important here. Okay. So if you do row operation on the identity matrix, then you will get some matrix that basically do row operation on this linear system. Okay, so I guess it's easier to see an example. So first example is, so we have 3 type of row operation, right? So first row operation is you interchange 2 rows. Okay? And for example, this is the result you get for exchanging 2 rows, the first and second row of the identity matrix. Right? Maybe, so you probably know, but let's write down. So remember the identity matrix look like this, right? 1 0 0 0 1 0 0 0 1 for 3 dimensions, and you exchange the first 2 rows, then you become this. Okay, and let's see that this matrix actually exchange the first 2 rows for any matrix if you multiply by left. Okay, so do E1A, then you see that the first row will be actually become a second row because it's picking up by this 0 1 0. So this one will be the 0 0 1 0 on this, and it will pick out A21, and this one will be the 0 1 0 on this A22 become A22, and similarly this on this, and again you this A23, and also this row will pick out the first row. So you see that the first row and the second row got swapped by this E1 matrix. And there is also something extra we didn't quite say, but also true. And or more like we haven't said why we want this, but this is also something true. Is you can also multiply a matrix by on the right by this E1, and you will see the second column and the first column and the second column got swapped. Okay, so this is a row swap matrix. And it corresponds to this elementary this row operation of exchanging rows. Then we have a second row operation that's multiplying a row by a non-zero element, and obviously then you will get this thing. So here is you multiply the third row by the number of 3, and you can see that you multiply this matrix on any matrix A, and you will multiply the third row of it by 3. And similarly, yeah, and similarly you apply this E2 on the right hand side, then you actually multiply a column by 3. Okay. So you can see that we can do all row operations by just multiplying those elementary matrices on the left. Okay. Although we already said 2 of them. But the third one we can also do. So the third one is you multiply 1 row and add it to another row. And so here we have an example, and this is I guess this is you multiply the third row by 3 and add it to first row. So it's once again our identity matrix. Then it's adding the third row 3 times to the first row. And once again, skip the calculation, but you can check it yourself. You multiply this on any matrix A, then you will add a third row to a first row. Okay, and similarly, if you multiply E3 on right, then you will actually add 3 times of first column to the third column. Okay. So question about so those are the definition of elementary matrix. Although we didn't, I guess we do have a very rigorous definition in this thing, but but yeah. So those are examples of how the definition actually applied. Okay, and how they look like. Okay, so 3 elementary matrix, and they will do row operation. And as we said, if you multiply those elementary operations on the left, then that's the thing we want to do, then it will do row operation. But also if you multiply by right, then it will do column operation. But we don't need the column operation for now. And anyway, elementary matrix, we want it to be doing row operation, and row operation, important thing about them is they should give you equivalent system. And we say that in this matrix algebra notation, equivalent system only happen when you are multiplying non-singular matrix. Okay, so it's important to check that those elementary matrix are actually invertible. Okay, so that we are getting equivalent system. So this is something we should prove, and I kind of prove in 1.2, but now we actually give rigorous proof. So we prove that all 3 kind of elementary matrix corresponding to all 3 kind of row operation is inverse, so they are non-singular. Okay, and so the inverse of the type 1 is itself is its inverse. So in change 2 rows, then you in change again, then you go back to yourself. Okay. And and the second type is you multiply some row, so you have alpha somewhere. You multiply some row by scalar alpha, then you want the inverse, you just multiply alpha over 1 over alpha on the row. Okay. And then type 3 is a little weird, so you add some row m times to another row, and the inverse, so is a bit non-trivial, but anyway it's in inverse, so you just add the minus m times, you subtract it out again. Yeah, so that's the inverse. And we kind of think about those in terms of row operation, but obviously you can do matrix multiplication to check that those are actually inversely one another. Okay. Okay, so now, so nice. We our theory is now sound. We play the sanity check and see that those row operations are invertible. So when we multiply, so those elementary matrices are invertible, and so if you multiply them on your system, you are actually getting equivalent system. So you can use them to solve your system. Okay. And okay, so we say a matrix is row equivalent to another matrix A if there are elementary matrices such that you can multiply those elementary matrices on A and then get B. So basically you can do row operation on A to get B, then we say B is equivalent to A. Okay? So yeah. So B, as we said, B is row equivalent to A if you can go from A to B by doing row operations. Okay, and and then we can say the excuse me. Yeah, then we can restate what we have in 1.2. So now we think about those linear system equation expressed by 2 augmented matrices, and so they are row equivalent. So So basically, we know the row equivalent if only if they have the same solution set, and then we rewrite those in terms of this matrix algebra. So Ax equal to B and Bx equal to C. Yeah. Oh, okay. Sorry. Yeah. Yeah. So basically, we are just restating things. So when we solve linear system, we know that those two things are row equivalent if they have the same solution set, and if you write in matrix algebra, then that means Ax equal to B and Bx equal to C are equivalent systems. So they have the same solution set on X. And also, this row equivalent, they have some algebraic property. So first is symmetric. So if A is row equivalent to B and then B is also row equivalent to A, because every row operation is inverse. So you can just do an inverse row operation, get back to A. And also, if A is equivalent to B, B is equivalent to C, then A is equivalent to C. So you can get B from A, you can get C from B, then you can get C from B from A. Okay, so it's transitive. But anyway, so that's row equivalent, and yeah. So you can also solve the linear system equation in this Ax equal to B form by multiplying all the elementary matrices. Okay, and so yeah, so for example, you can also do the Gaussian elimination with the elementary matrices. You're basically doing the same thing but with a different notation. Okay. If not, no question, then okay. Then let's go to the most interesting part of this chapter. But before that, let's do a little warm up. So I guess more like a little review on logic. So we say we have an if only if statement here. So what is this? So in logic there are actually three kinds of statements between two expressions. Okay. So there is this if and only if and if and only if. So for example, we have a statement Jake will eat the fruit and it is an apple. So first expression A and second expression B. And what do we mean by Jake will eat the fruit if it is an apple? It means the second expression is it is an apple will imply the first expression. Okay. And this is called B is a sufficient condition for A. And the other one is kind of a negation of this. That's never mind. Yeah. So Jake will eat the fruit only if it's an apple. That means that when Jake eats the fruit, then that means that fruit must be an apple. So the first expression A will imply the second expression B. It means B is the necessary condition for A. And then there is if only if, and often we will shorthand it as IFF, and that means that those two statements are the same. So it's the first one and the second one together. So A will imply B and B will also imply A. So and we call that B is a necessary and sufficient condition for A. And then there is some negation rules on logic. Hopefully you still remember. So A imply on B doesn't mean B imply on A, or negation of A imply negation B. So this is only true. The equivalent statement is this called contrapositive. It means not B imply not A. Okay. So A imply B means not B imply not A. And but if you have only if, then most of the things are the same, because A if only if B is the same as B if only if A, right? Because these two directions, and you solve both doesn't change. And then you take the contrapositive of both of them. That also means not B if only if not A. And here we have copy paste too much. Forgot to change. So this should be not A equal if only if not B. Okay, not A if only if not B. Okay, so this is basic logic, and here we have some warm up. So we have this strip statement: if and only if only if, and we want to skip this. Yeah, and here we have some statement down here, and you can see which one of those they are equivalent. I guess maybe yeah, and yeah, let's maybe try the first one. So we have A and B here, A and B. So we have that the first one is not ample, so we have not B, and imply not A. Okay, and yeah, not B imply not A, and I would say the contrapositive of A imply B, so that's the first one. Okay, so this is one, and hopefully you can do similar thing to other statement. Okay. Anyway, that's a review of logic, basic logic, and people okay. Okay. I think that's enough logic. Let's go back to linear algebra. Okay. And we want to talk about singular matrix, or more like non-singular matrix. Okay, so we have a nice theorem here. So A is an n by n matrix. Then we have three conditions that both say that A is non-singular. So first is A is non-singular. And then we have that Ax equal to 0 has only the trivial solution 0. Okay. And A is row equivalent to I. Row equivalent, once again, means that there are elementary operation on A that can turn it into I. Okay. And those three conditions are equivalent, and we have a proof structure that will go this. So we will say A will imply B, and B will imply C, and C will imply A. And then we have this logic circle, and every one of them are if and only if. Because you can get, so you can go from A to B like this, and then you can go B to A with this. Okay, and similarly, so each one of them you can go to each other, and so those three statements are all equal to each other. And then we have another corollary that you can prove from this theorem. Okay, and yeah, so let's see this. So let's see these three proofs. So first, one is if A is non-singular, then Ax equal to 0 only have a trivial solution. And yeah, it's pretty direct. So A is non-singular, there is A minus 1. So that means that if you apply this Ax equal to 0, so you multiply A minus 1 on both sides, then this A minus 1 times 0 is still 0, because everything times the 0 vector becomes 0. And I guess we didn't prove this, but it's pretty easy to check. And then on the left hand side, you have A minus 1 on this thing, then A minus 1 will cancel your A, and then you just get X out. So you see that X equal to 0. Okay. So if A minus 1 exists, then this Ax equal to 0 solution is always 0. Okay? Okay, question. So this is more tricky. But yeah, so that's a proof. And the second one is quite long. Okay, so this is the hardest one. Okay. So it's Ax1 has only trivial solution. Then A is row equivalent to identity. Okay. And here we have a very constructive proof. So, excuse me. Anyway, so we start with Ax equal to 0, only have a trivial solution. Okay. And so we have Ax equal to 0. Then we use our elementary matrix. Okay. So we can multiply the excuse me. We can multiply the elementary matrices on this Ax equals 0 to try to solve it. And so how we solve it is we excuse me. Yeah, we multiply a whole bunch of elementary matrix, and then we get A equal to this reduced row echelon form. Okay. So yeah, so you can always do this because we argue that we can do this in chapter 2. Sorry, in 1.2, and yeah. So you use row operations, you get A equal to reduced row echelon form, and now the row operations are expressed as elementary matrices. So multiply a whole bunch of elementary matrix, and you get A equal to this reduced row echelon form. And obviously the right hand side should still be 0 because you are multiplying 0. Okay. And then because we are multiplying elementary matrices, so this system should have the same solution set as this system. Okay, so that's important. Those two things are equivalent because you are doing elementary matrix operation. Okay, and so they have the same solution set, and now here we use this condition. So this thing only has with the trivial solution, means the number solution of this thing is 1. Okay, so this thing only have trivial solution, and this is the equivalent system. So ux equal to 0 only have the trivial solution. Okay. And but now this is reduced row echelon form, and we can think about its free variable and lead variables, right? So remember, reduced row echelon form kind of look like this. So we have those echelons, and they have ones. So you have those leading ones are lead variable, and some of those free and you have like free variable like this. Okay, but okay, but if you have a free variable, then if you have a free variable, then you must have infinitely many solutions. You cannot have only one solution. Okay, and yeah. So, but we only have one solution. That means there is no free variable in U. Okay, so every variable must be a lead variable. And now we're back to remembering that A is an n by n matrix. Then it's kind of I guess counting. So you have no free variable, then you have n lead variable. There are n columns because there are n columns, and you also have n rows. So so it can only look like yeah. So this is on geometric thing. So you have no free variable, then you are just like this going down 1 by 1 by 1 by 1. But you are square matrix, then you must be just this 1 0 0 0 1 0 0. Okay. So yeah, so this U is the identity. So we have found how and obviously U is getting from it. We can get U from applying elementary row operation on A, and yeah. So we have a constructive example of how A is row equivalent to I because this U equal to I. Okay. Any question? Okay. And no question. Then finally the third one. Okay. So A is row equivalent to I, then A is non-singular. And this one is also simple. So A is row equivalent to I, then we have a whole bunch of elementary matrices that you oh, sorry. Anyway, it's transitive. Okay, so A is row equivalent to I. Oh, it's symmetry. So A is row equivalent to I means there is, okay, we're actually writing this in the other way. Let me see. Anyway, A is row equivalent to I, then you can multiply a whole bunch of elementary matrix on I to get A. And so A just equal to those whole bunch of elementary matrix multiplying together. But as we say, the elementary matrices are invertible. So their products should also be invertible. So now we have a constructive answer. So a minus 1 just equal to all those in minus 1 in reverse order. And then we see that a is non-singular because we have inverse of a just written here. Okay. So this is the most technical quadrant. Sorry, the most technical theorem here in the chapter. So any question? Yeah. So I guess let's see an example of this theorem, although in kind of negation. So remember this theorem says these three things, okay? So these three things imply each other. They are if only if to each other. And because they are if only if to each other, so an equivalence theorem is we can negate all three expressions, okay? So we say those three equivalent to each other, then equal to these three equivalent to each other, because it's if only if to each other. And as we say, if only if, then you can negation, then it's the same statement. And anyway, so what if we negate all those three? So it's a is singular, and this one says ax equals 0 has non-trivial solution, and the negation of this is a is not rho equivalent to identity. Okay, and here we have an example of the singular thing. Okay, so what our theorem is trying to avoid is singular a like this. So remember we say this a is singular. So a is singular, and why does ax equal 0 has a non-trivial solution? It means that, so here we can see an example. So this 0 here is being funny because you multiply a with 0, 1, then you see it's 0, 0. So this 0, 1 is a non-trivial solution to ax equal to 0. And why is a rho not rho equivalent to identity? Okay, it's a little hard to prove. But basically, you think about you do row operation on A, you are doing basically linear combination of rows, right? And so this column will just, so on the second column, you will just get a linear combination of these zeros. And linear combination of 0 can never get 1. So if you want to get identity, okay, let's draw better. So if you want to get identity equal to 1, 0, 0, 1, then you can never get this 1 here, because on the second column you only get 0, then you can not get this 1 on your identity matrix. Okay. So yeah. So you see that, but obviously we didn't prove this because we only give an example. But hopefully this example give you some intuition of why a singular matrix will give you a non-trivial solution, and why does it not rho equivalent to identity, because it is this kind of 0 that you cannot get rid of. Okay. Okay, so that's a little digression that the book doesn't have. Hopefully it don't confuse you. And okay, let's go back to the book. And we have corollary 1.5.3. And it's very similar to the first two statements. So the first statement we say a is non-singular if only if ax equals 0 only have the trivial solution. And here, okay. So the corollary 1.5.3. So you see we have two conditions that are equivalent. So first is a is non-singular, so this is basically the a there, okay. And but the other condition we got changed. We say that ax equal to b has a unique solution. So it's not 0 here, okay. So here things change. We say, yeah, but it still only have one solution, but it's not 0 because b is not 0, okay. And okay, but this color is a little weird because we didn't quantify b. But I guess for some b. Okay, so let's hand wave through the quantifier on b for now. But anyway, so you see that we have kind of condition B prime here. Okay. So we change this expression to one that's not very rigorous because we didn't quantify B. But anyway, we can still try to prove this. We say those two conditions are equivalent to each other if we fix on B, I guess. So we fix on B for now. But I guess, yeah, we can probably say for yeah. So let's write this for this vector B, and these two expressions are equivalent. Okay. And yeah. Okay. So as we say, the if only if has two directions. So we should prove this A expression to B prime and the B expression to A prime. Sorry, B prime expression to A. And so let's do the easy direction first. So if A is non-singular, then AX equal to B has the non-trivial solution. And that's basically the same as this proof. So if you still remember how we go from A to B, is we multiply by this A minus 1. Because if A non-singular, then A minus 1 exists. And so we just say AX equal to B has on the solution. Then we multiply A minus 1 on both sides. Then we see that this X hat is just A minus 1B. But A minus 1 is unique, B is unique. So A minus 1, B is just some vector, a unique vector here. And so this X hat is a unique solution. Okay? And okay, then the other direction is a little funny. So we want to say if AX equal to B has a unique solution, then A must be non-singular. And we kind of do the logic a little. So we kind of want to do contrapositive, but while returning in a funny way. Okay. So yeah, I guess I'll just say this, we are proving contrapositive. So we say if A is singular, then we want to say AX equal to B has more than one solution. Okay. And so how does this go? So A is singular, and suppose A is equal to 0 has some solution. We are already using. Excuse me. Oh, never mind. Yeah. So A is singular. Then we know A is equal to 0 has a non-trivial solution. This is back to, okay, so this is back to here. We are doing the negate version of 1.5.2. So A is singular, then AX equal to 0 has a non-trivial solution. Okay. So AX 0 has some non-trivial solution Z. So Z is not equal to 0, but AZ equal to 0. Then and then we can get another solution on AX equal to B by adding this Z on your X hat. Okay, so this is the important part. You can add the solution for your, and this is something actually people do a lot of time. It's very interesting. So you have this system A equal to B, and you can write another system A equal to 0. So you can write a homogeneous system. Then if you add the solution of the homogeneous system, this Z, to the solution of your original system, you will get a solution of another solution of your original system. This is something that we do actually even outside of this course. Like in signal processing, we also do this. Okay. So anyway. Yeah, so you add the solution of this homogeneous system, is AX equal to 0, to your original system AX equal to B. Then, okay, and now we say because Z not equal to 0, so Y is something different from X hat. Then you see that AY is also equal to B because now you just write out everything linear. So y equal to x hat plus z. So ay equal to ax hat plus z. And at the beginning of this, today we say the matrix multiplication is distributive. So this is ax hat plus z equal to ax plus az, and ax hat plus az. And ax hat is a solution for this equation, so it should equal to b. And az is a solution to this homogeneous equation, and it should be equal to 0. So that's b plus 0 equal to b. Okay? And yeah, so we see that this ax equal to b has another solution on y that's different from x hat. So it has more than one solution, so it doesn't have a unique solution. And so we prove the contrapositive. And so a singular means that ax equal to b has non-unique solution, and that means ax equal to b has a unique solution, and a must be singular. Okay. And yeah, but here we are in a little different structure. We say we want to prove this, and yeah, anyway, yeah. So we say if this is not true, then we get a contradiction, so this must be true. Okay. Any question for all those logic? So yeah. So obviously this 1.5.2 is important. So how you characterize a non-singular matrix or a singular matrix? We are going to see usually we actually usually characterize in terms of a singular. But anyway, those conditions are important that you should remember. And yeah, and in a later part of the course, we are going to see more conditions about how to say a matrix is a singular or non-singular. For now, you have those three, and don't forget the basic definition. So I guess the first one is the basic definition. So there exists a minus 1. Okay. So just as a reminder, non-singular means there exists a minus 1, such that a minus 1 and a equal to identity. Okay. And then the non-singular means that when you solve ax equals to 0, only have the trivial solution. And also a can be multiplied by, can be turned into identity matrix by the row operations. Okay. Excuse me. So that's singular matrices. And yeah, and here something interesting. Interesting operation you can do is if the homogeneous system has non-trivial solution, then you can add it to the solution of the original system, and you can get more solution. That's something interesting. But yeah, that's corollary 1.553. So instead of a is equal to 0 has a unique solution, you can just say a is equal to b has a unique solution. Okay. If not, then yeah, let's see a little more thing. And here, so from the proof layer, we see a way to compute a minus 1. So for any non-singular matrix, then because a is row equivalent to identity, so you can find the inverse of a. Okay, so this is actually very inefficient, but it's one way. So you can find the inverse of a by just thinking about the row the elementary matrix. So you can do those elementary matrix or row operation of a, and on a to turn it into identity. So basically do Gaussian elimination here, and then think about those elementary matrices. And yeah, and you find out this string of the matrices are just the inverse of a. Okay, so what do I? Yeah. Yeah. So this thing is the inverse of a because you multiply them on a equal to identity. So I don't even need a second line. And yeah. Okay. And And we can do this in, I guess, more efficient form. So this is some calculation notation to make the calculation easier when you actually want to do this. Okay, so we can write the, I guess, augmented matrix, although this is not how we'll define augmented matrix because this was a vector, but we kind of extend the definition of augmented matrix. Anyway, so if we put this A matrix and the identity matrix together, side by side, then we can run the Gaussian elimination to get identity and A-1 in kind of a nice way. I guess it's a little easier to see an example. And so this is a way to calculate A-1. So for example, you have A equal to this. Then first we write down this augmented matrix. So you have A here and identity matrix here. And what we try to do is we try to do Gaussian elimination. So we want to do row operation on this whole 3x6 matrix. And we want to turn this side equal to identity. And when you complete turning this side to identity, then the other side will be A-1. Okay? So, but we are a bit lazy, so we skip the important step. But let's see the first step. So we want to do Gaussian elimination, right? So first we want to turn those two elements to 0. So add 1 times of the first row to the second row. So add 1 here, it becomes 0, then 4 plus 2 becomes 2, 3 plus 0 becomes 3. And then we also do the same thing on the identity matrix. So 1 add here, so you get 1, 0. This is 1, 1, 0 here. And similarly, you get minus 2 times from the first row to the third row. So you get 0 here, then you get minus 6 and minus 3. And you get minus 2, 0, 1 here. Okay? So you keep doing this, and you do a row operation until this side become identity. Then the other side, yeah, you can think about you multiply all those EI. And so basically all those EI multiply on this, make this into identity. And the other side will just be the product of all those EI. And so when you complete this, you will get A-1 and it's some matrix. Okay, and yeah, similarly, and then you have this A-1, then you can use it to solve linear system. So we have a linear system where the A is this A, and they just multiply A inverse by both sides, then you see X is the A inverse on this B. So A inverse on this B is this thing. Okay. So this inverse matrix is nice because then now you can use them to solve the linear system. And actually it's solving it a little better than what we had before, right? Because this is solving. So interesting thing is this A-1 only depends on the coefficient part of A. So once you get this A-1, then and you can kind of swap this B around. So any B you can just multiply by this A-1 and get the solution set. But also there's some restriction here you see because we only define A inverse on square matrix. So the number of solution and the number of equation must be the same for you to have A-1. And obviously this needs to be invertible. So it's quite a restricted way to solve the linear system. Only works when you have a unique solution and you have this n by n. Yeah, I guess only n by n system can have unique solution anyway. Okay. So this is how you use invertible matrix to solve this system with unique solution. And finally we have, okay, I have 10 more minutes, right? And finally we have a little more definition, and it's, well, basically just definition, but definitions, but we'll use them every now and then. So we have upper triangle, means, well, it looks like a triangle on the upper part. But if you want to go technical, it means this lower part is 0. So Aij for I bigger than j is 0. So basically the lower part, so the diagonal can have non-zero, and everything lower than diagonal it should be 0. And similarly, you have lower triangle, so you have this thing where the lower part can be whatever, but everything above the diagonal should be 0. Okay. And yeah, so either one of them we call it triangular. And also there's diagonal. I think I kind of say this sometimes. But anyway, diagonal means only the diagonal part is non-zero. And obviously you can still have some zero somewhere in diagonal, but only non-zero part are here. So all of diagonal, so all those I not equal to j coefficients are 0. So it's diagonal. And by definition, so diagonal is both upper triangular and lower triangular because you have those zeros and those 0 here. Okay? Oh, we're super fast. And I guess 10 minutes, can I finish? Maybe you can finish this chapter today. But never mind. I guess we'll stop early. But anyway, so here we have the checklist. So remember we have elementary matrices, and they're corresponding to the 3 elementary row operation. So the elementary matrices are the matrices where if you multiply then on the left of your matrix, then you will do the row operation on the matrix. And remember they are invertible. And then we define this row equivalent of 2 matrices. Means that there exists a string of matrices that you multiply them on A, then equal to B. So we have tons of whatever. Why don't we write it down? So there are E1, E2, EK. A equal to B, then A and B are row equivalent. Okay. Means, yeah. And then we have a lot of conditions for non-singularity. So non-singular means, first by definition, non-singular means the matrix is invertible, and they only defined by n matrices. So I guess that's jump back because why not? Of time. So once again, we have those 3 conditions. So A, n by n, and non-singular means invertible. Then it also means that Ax equal to 0 only have a trivial solution, and A is row equivalent to identity. Okay. And yeah. Wait. Why? Oh, okay. And yeah, we also have the 1.5.3 where we say instead of Ax equal to 0 it has a unique solution, we say Ax equal to B has unique solution. And yeah, then finally you have those 3 definitions. We don't do too much with them, but they are definitions that's nice to remember. So upper triangular, lower triangular, and diagonal. And yeah, I think that's for today. So if any question, you can ask me after class, or I guess you can ask me right now, or that's stuff for now. Okay. Okay. So yeah, see you on Wednesday.